So the next talk has the subject, the nextpnr FOSS FPGA place and route tool, and it will be given to you by Clifford Wolf, who is a very active member of the project IceStorm, and whoever listened to the talk before already got step-by-step introduced to his work. Basically, he will tell you now something about an open source FPGA toolchain. So give a warm hand of applause to Clifford Wolf.
Thanks. So I'm going to talk about nextpnr, which is our next open source place and route tool for FPGAs. So to get us started, I'm going to talk about the ecosystem of open source place and route tools that we have right now. FPGA place and route tools. There are obviously a couple of ASIC place and route tools as well. So there is VPR, which is about 20 years old. It has timing-driven algorithms. It's fairly portable in terms of porting it from one FPGA architecture to another. But the focus of VPR is more on architecture exploration, so it allows you to easily try out different variations of your interconnect architecture, things like that. But it's not really aimed at creating bit streams, creating placements and routes for real-world FPGAs, because the real-world FPGAs, they actually are not as regular as the made-up FPGAs that VPR is targeting. So we needed something else to not only do architecture exploration on theoretical devices, maybe do some experiments for new placement of routing algorithms. But for targeting real devices, we needed something else. So when we did Project IceStorm, we wrote our own place and route tool just for that, which was called ArachnePNR. By now, it's about 3 years old. It was not timing driven, so it would just create a valid routing, a valid placement for your design, and afterwards you could run timing analysis and you could learn how fast it is, but you couldn't really tell the tool, actually this net should meet this timing constraint, so please take this into consideration when you place stuff, when you route stuff. And it really only supported ICE40. So we thought about maybe taking ArachnePNR and extended it to more timing-driven algorithms, to architectures beyond ICE40, but it was really written just dedicated for the ICE40 architecture, and it was not really meant to be a portable tool. So given this situation, we decided we want to have a new place and route tool that we can use on our way forward to creating open source tools to target actual devices that you can buy, development boards that you could use. So we started nextpnr. It's brand new. So we started working on this year. It's timing driven. It's very portable. And it's a team effort, which is completely new for me. So if you follow my projects, usually my projects are I lock myself in a dark room for a couple of months and then I emerge and say, look what I've done. But now we have a couple of people all working on that, and it's a really great experience for me. One of the things that we get when it's not just me fiddling with something, but a team of people, we get the kind of features that I'm not really good at implementing. So for example, we have a GUI, and you can actually see the schematic of the device and zoom in, and I'm going to show you this. But of course, it still works very well with makefiles, and of course, most of the projects never use the GUI. You just run it in a makefile or a shell script, and it does what it's supposed to do. There is an API for supporting new architectures, which is a dissimilar approach to what many other tools do. So the regular approach would be to have a common data structure, and you just have to create this data structure in memory that describes your target device. We don't have that. Instead, every architecture backend must implement the same API, and then this API is used by the algorithms to access the architecture database. And the reason we do that is because we think, or I think, that one in-memory representation might not be universally a good representation for all different target devices that we want to support. And I'm going to talk about a little bit on the later slide. So right now we have support for ICE40 and ECP5. So these are the things that we actually recommend you to use. There are also some other things that are ongoing. So we have a so-called generic target. I'm not quite sure if it actually builds right now. It might have bit rotted a little bit. But the idea is that you can use this to generate a architecture database on the fly using a Python script. And with this, we can also cover a little bit the architecture exploration aspect of things. We also have a experimental binding to Torque, which allows us to do place and route for 7 series Xilinx devices, for example. But those are the things that we don't recommend everyone out there use. This is more the kind of stuff that we encourage you to have a look at if you're really interested, and maybe if you would like to spend some time improving those things yourself. But as a user, right now we are good for generating designs for ICE40 and ECP5. Yeah, and some of the future, all of those future plans here are already implemented. So this is a reused slide. So we have floor planning now. We support multi-clock designs. We do support complex constraints like relative placement constraints and stuff like that. Okay. So this is actually supposed to be a video, and I spent the last hour S-tracing GStreamer to figure out why it doesn't really work. But I guess you can see what the video shows. So just to demonstrate you that we can actually do non-trivial designs using these tools. So this is an example for ICE40. On the ICE40 side of things, we support all of those devices here. And we have a full Verilog to bitstream flow. So we use Yosys for synthesizing the design, and Yosys in this setup will generate a JSON file, and then this JSON file is read in by nextpnr, and nextpnr will create one of those .asc files for iStorm, and then iStorm will read that file and generate the actual bitstream. The board that you see in this non-playing video is an Icebreaker FPGA board, and it's the board that we are right now pushing. So there's a crowd supply campaign right now that we are pushing as a platform for teaching people FPGA design. So we've worked with a couple of different dev boards over the last few years, and then we took all the beefs we had with the different development boards and created a list of requirements. What we think a good dev board should have be if the target application is not necessarily prototyping commercial products or something like that, but instead if the application is teaching people FPGA design from scratch. And personally, I really like ICE40 as an architecture for that, because ICE40 is a fairly small FPGA. Because when you do some teaching projects and you have a ridiculously large FPGA, people can write ridiculously inefficient designs and it will still fit. And they will never learn that actually your 7-segment decoder should not take 150,000 gates. Whereas with an ICE40, you can actually set a goal that is a little bit challenging for the size of the device, and then people have actually to learn how to make efficient designs in order to achieve that goal. Okay. So here's another video that doesn't play. This one demonstrates that we can work on an ECP5. So we have support for, I think, for all of those devices, but David will know it better. And yeah, we have a full Verilog to bitstream flow again. So we can use Yosys for synthesis. Again, this will generate a JSON file, and then we can read that JSON file in nextpnr. nextpnr will do place and route. And then we're using the Project Trellis infrastructure for bit generation and actual device programming. And in the video that doesn't play, you actually see Linux running on an SoC running in that FPGA, just to demonstrate that we can actually do place and route for fairly non-trivial designs like a Linux-capable SoC. And if the Linux would play, you would actually see that we can use shell commands to turn on and off the LEDs on the dev board. Okay, so this video apparently starts with a black frame, but that video just shows an Xilinx dev board blinking to convince you that we have also support for the Xilinx devices. There is a reason why the video that you don't see shows a little blinking example and not Linux-capable SoC, because right now we still have a couple of timing issues to figure out with targeting the larger FPGAs. But we are working on that, and I'm very confident that by the end of next year, we might have completely different things where we say, oh, this is the stuff that we can't do yet, but this, of course, not a big deal. Right now, because this is based on Torque, I should tell you what Torque is. Torque is a library that can be used to do place and route experiments, I would say, for Xilinx devices. And this will generate a so-called XDL file, which is something that you can read into the older Xilinx tools, the ISE tools, to actually generate the bitstream. So we don't have a full end-to-end open source flow here right now. However, what we have is something that picks out the difficult part for the context of nextpnr, which is actual place and route. And only for the bitstream generation, we need to defer to ISA in this case, but it shouldn't be too difficult to set up something similar using the Project X-Ray database and or using Xilinx Rapid Write, which is a rather new thing from Xilinx that would allow people to generate custom bit streams. Okay, screenshot. We will see more of the GUI at the end during the demo. This is what it looks like when you run it in GUI mode. We have a device view. In this case, it's a placed and routed design, so we can actually see the placed cells. We can see individual nets. Just to make the screenshot more interesting, I decided to color some of the nets in. The thing that we see on the left is a carry chain, for example, the magenta nets. You see we have a console window where you see the stuff that would just be visible on the normal terminal console if you wouldn't start it in GUI mode. And at the bottom you can see this is actually a Python shell, and that would allow you to access all the internal data structures and kick off all the algorithms and stuff like that. And the right-hand side of the screen is dedicated to something that will allow you to investigate both the device database that describes the architecture that we are targeting, but also the netlist that we are trying to implement on that architecture. So bells, wires, pips, that would be the device-specific categories of objects, and cells and net, that would be the netlist. Few words about the overall architecture of nextpnr. So we have a couple of what I would call front-end components. Some of them are common, which means shared between different architectures, and others are architecture-specific. So, for example, the code that can read a netlist is common. We need the same code to work for all the architectures. But the packer, for example, where we take individual, for example, lookup tables and pack them into larger logic cells, this is something that is architecture-specific. Every architecture would need its own packer. And of course, we are trying to design nextpnr in a way so that we can move as much code as possible to the common bits and reuse them in the architecture-specific bits. So on the one hand, for each architecture, you will need to write your own packer, but then on the other hand, we try to provide the infrastructure that makes it fairly easy to do so. Yeah, then there is a router, of course, and the placer, but they might be interleaved with similar things that are architecture specific. So in a couple of scenarios, for example, you might have different routers. You have architecture specific routers that do specific clock routing tasks or things like that, and then you might follow that with the generic router that routes all the ordinary nets that are remaining, depending on what is good for you, the architecture that you're targeting. And those architectures, they access a database that contains the design that we are placing right now, the netlist, and it accesses the architecture database through this architecture API. And that means that the architecture database itself can be stored in a very different way for different architectures. And this is indicated in this picture. We see we have a couple of different implementations of that architecture API. But then we have even more architecture databases, because we might have one architecture that has one implementation of the API, but then 5 different databases in the back for the 5 different device types that are available in the family that we are targeting. Okay, so I have 2 slides about nomenclature that we use within nextpnr. It's not so much because I'm going to use this nomenclature a lot in the slides that follow, but more to give you a better impression about what are the kinds of objects that we are managing in nextpnr. So that's the reason why I'm talking about this. So there is the design database. That's the netlist we would like to implement on the target architecture. And in this thing, we have cells, which are just the things like lookup tables or logic cells or flip-flops that you can instantiate on your target device. And each of those cells has 1 or more ports. I guess most cells have more ports, but there are some that actually have only 1. And then those ports can be connected to nets. And this net, of course, can be connected to another port of another cell, and that's how we see the connectivity of the entire design. When we are looking at a specific net, there is one port on one cell that is driving that net, and we call that a source. And then there are more other ports from possibly other cells, and we call those sinks. And each net has exactly 1 source, but it can have an arbitrary number of sinks. And a source-sink pair, we call that an arc, and that's a very important entity in the routing algorithm, because the nextpnr routing algorithm is actually prioritizing individual arcs, whereas VPR, for example, can only prioritize nets as a whole. Okay. So this is the design database side of things, the objects that we can manage here. And then there is the architecture database. The big distinction here, of course, is that the architecture database is static. So I say I would like to target this or that part, and then it's always going to be exactly the same database. Whereas when with each run of nextpnr, I might give it potentially a different netlist and a different design to implement. Okay, what kind of things do we have in the architecture database? There we have bells, short for basic elements, and these are the actual things that physically exist in your FPGA. So the placement part of place and route essentially is finding an assignment for each cell in your design to a bell in your chip. And similar to the ports on the cells, we have pins on bells. Then we have wires that make up the interconnect of the chip. And we have ways of connecting those wires together in a very dynamic fashion. And those things are called PIPs, programmable interconnect points. So each PIP essentially has like a source wire and a sink wire. And I can activate a PIP or deactivate a PIP. And Similar to placement being creating a mapping between cells in your designs and bells, routing means creating a mapping from all the nets in your designs to wires and pips on the chip. And then there is another thing in our architecture database, which is called groups. And groups are not used by anything except by the GUI. They are just a means to group things into larger units. So usually when you look at an FPGA, depending on the vendor, you might have organizational units like slices, and then a couple of slices make up a tile, and then those tile maybe make up a column and stuff like that. And you can use those groups to preserve this kind of structure in the GUI. So say you have a FPGA, you built your own FPGA, you documented an FPGA, something like that, and you would like to add a new architecture to nextpnr. What would that look like? So the first thing you would need to do is create a new top-level directory in the nextpnr code base, and add a little bit of CMake magic to make it appear as architecture. And then in this directory that you created, you need to add at least two files. One is called archdefs.h and the other one is called arch.h. And archdefs.h contains a couple of data types that are architecture specific. For example, one of those data types is called bell ID. And different architectures might use different underlying data structures to represent the bell ID. So on one architecture, it might just be an integer. On another architecture, it might be a struct with an X and a Y coordinate identifying a tile. And then another integer that is like the bell index within that tile. And we want each architecture to be able to use like the most compact representation possible in that architecture without losing the flexibility that we need to support really large devices. And the way we do that is by making all those data types architecture-specific data types. And then each architecture can choose whatever they want, and the C compiler will try to do its best to actually implement the thing, C++ compiler. So arch.defs, that's where the data types go, and then arch.h, that's where one big class goes, which is called arch. And this class has to implement about 100 different methods that are this architecture database API. And then you might need to add a couple of additional files, C files with additional functions for your architecture. The most important one here might be main. Because we actually don't have one main function for nextpnr. Instead, so when you run CMake, you tell CMake what kind of nextpnr implementation you would like to build. There's one binary nextpnr-ICE40 and other binary nextpnr-ECP5. And each of them has a different main functions because we might have different command line arguments and stuff like that specific to different architectures. Okay, so this architecture API, it's settling down right now. We haven't changed much lately. There are still a few things that I want to change. Long term, we need to freeze it somehow, but it's still a little bit moving. So don't implement like 100 architectures at the same time right now. Go at it slowly, one by one. Also, with each architecture we add, we might identify a new thing that we actually need as functionality in that architecture API. Because of that, we are trying to implement one architecture after the other rather slowly, but we also want to cover a lot of different spots in the overall FPGA design space so that we are sure that we have all the functionality in place by the time we say, okay, this is now the frozen, 1.0 version of this API. Okay, so implementing about 100 methods sounds like a lot. But the thing is that those methods are very, very basic. So in many cases, you have something like your in-memory representation of the architecture database. And then each of those functions is maybe 2 or 3 lines of C code, just doing a little bit of point arithmetic to look up the right thing in the memory and then read whatever the thing is that you're querying with the function. Because there is no get bell info function, for example, that would give us all the information about a bell. Instead, for each attribute that you might be interested in, there is a different getter method. And because of that, we have a lot of methods that you need to implement, but each of them is relatively simple and small. Okay, so say you would like to implement your architecture backend for nextpnr. You would like to write this 100 methods. But first you need to figure out how to store the information in memory that makes up your target architecture database. We think there are three main approaches how to do that. But the nice thing is we have a very generic architecture. So if you identify a fourth method that's not on the list, then hopefully you can hide this fourth method behind the same API and everything is fine. So the three methods that we think are relevant are a completely flat database. So that means we have an explicit entry in our database somewhere for each and every wire, for each and every pip and each and every bell in our device. And that means if the device is twice as large, the database is twice as large. But it also means if my device is super irregular, then we can also just implement it here and have a flat database for a very irregular architecture. And we use a flat database for ICE40, simply because the ICE40 chips are small enough so that it makes sense to just have a flat database. But as you can imagine, when your chip becomes larger and larger, your database becomes larger and larger. And at some point, this is not really feasible anymore. So there are two different approaches to solve this issue. And the next step would be to have a deduplicated database. The basic idea behind a deduplicated database is that we first create a flat database, and then we look in that flat database for regularities. For example, a wire with a certain layout or structure, and maybe there is a separate wire with the same physical geometry, just one tile to the right. And then we can merge these two entries, and we only need that once in our database, referenced from two different locations. The nice thing about the deduplicated database is that you can still start with a flat database. So if your chip has a couple of irregularities, you don't need to do anything special. Whenever there is an irregular structure on your chip, it will just fail to deduplicate it and everything will be fine. But the downside is your chip must be at least small enough so that it's feasible to generate a flat database in the first place. And then we can deduplicate it. And for really large chips, that's not really an option. So for really large chips, you have to use a different approach, which I call a tile-based database. And with a tile-based database, you say, this is the tile structure behind my chip. And I have a small database, in essence, for each and every tile type. And then I just have a large table that tells me which tile in my chip is of which type. And the nice thing here, of course, is if your device is twice as large, the database is only a tiny bit larger. And if you have two different devices in your chip family, the database that covers both of them might only be a tiny bit larger than the database that covers only one of the two. And yeah, right now we are using ICE40, a flat database for ICE40. For ECP5, we use a deduplicated database. And the long-term goal for support for Xilinx 7 series devices is a tile-based database. Okay. There's a Python API. Who here has written things in Tickle at one point in their life? Who feels bad about it? Yeah, so we decided we don't go with the industry standard. We don't have Tickle. We just expose everything we have to Python. That will make it easy to do prototyping of algorithms, stuff like that on the one hand. You can just try stuff out in Python first, and if it really works, then you can see if you can make it perform better by rewriting it in C. But we also use Python for constraints, essentially. So there are some simple constraints that you can set, like this clock constraints here that tells the tool what the clock frequency is on different clock nets. But you can also write actual code in Python that does stuff like iterating all the cells in the design and then checking if those cells have a certain attribute set. And if they have a certain attribute set, then add them to a certain placement constraint. I think that this is much more flexible than other approaches, especially if you have larger designs and constraints where it's really hard to explicitly write a list saying this should go here, this should go there. Instead, you would like to have a small program that just looks at the design and then extracts the placement information from other hints that are already there, using things like cell attributes or just hierarchical names of objects in your design. So, what are the next steps for the project? First of all, of course, we would like to slowly replace ArachnePNR as the main place and route tool for IS-14 Project IceStorm. I think we're actually quite far with this. Many of the things that use Project IceStorm are already switching to nextpnr. We don't want to be too aggressive about that because when everyone switches at once, we get like all the bug reports at once. But I'm fairly happy with the rate of progress for moving people from ArachnePNR to use nextpnr. Well, of course, there are many ideas that we have how to further improve our placer and router. Some of them are driven by concrete needs that we, for example, look at the results that we get on Xilinx and then say, okay, we need to fix this and this and this to make it work as good as we want it to work. And other of those improvements are just ideas, stuff that we would like to try out. And of course, this is also something where we are looking for other people using this, for example, as a basis for academic research and many other things. So if you have any ideas how a placer should work, how a router should work, and you would like to try out if it's feasible to actually build a placer or a router that uses this kind of algorithm, then hopefully nextpnr is a good framework to do this kind of experiments yourself. Yeah, and of course, support for more architectures. The whole point is that we want to have something that is portable to many architectures. So we will just add slowly one architecture after the other. And we hope that long-term we can do that with actual support from vendors. So we don't have to start by staring at bit streams and figuring out what individual bits do just to support stuff in our place and route tool. Yeah, and once we got that, hopefully we will have world domination for the small world of FPGA place and route tools. Yeah, some comparisons between ArachnePNR and nextpnr. So this is nextpnr bench. Right now there are only like a couple of designs in there. And these are like 10 runs with each tool with random seed values, and then the average. So you can see on the left column in this table in the center, the maximum frequency. On average, nextpnr has a 30% better timing results than ArachnePNR, so that's definitely an improvement. But on the right-hand side, you see on average it's like 50% to 100% slower than ArachnePNR. I guess that's the price you pay for actually doing everything timing-driven. But I have something more about this in the demo as well. So this here is nextpnr against ArachnePNR. So we still do bug fixes in ArachnePNR, but for the most part, ArachnePNR is like a pretty stable artifact. So we are comparing the quality of results in terms of maximum frequency against ArachnePNR on more or less regular intervals. You can see more or less whenever I have time to run the scripts. And yeah, you can see it's kind of improving. So I guess if we can keep up the overall rate of improvement for like another year, then we will produce designs that are faster than physically possible. So yeah, we can't keep up that rate of improvement for another year. We're already pretty close on what can actually be done. Okay, it's time for a little demo. For this, I need to change my settings a little bit. Hopefully that works. Okay. Yes, so we can both see the same thing now. This is not large enough. How is that? Good. I can only see the people in the front, and the people in the front tell me it's good. So. So the first thing I'd like to show you is this here. So that runs users to run synthesis for a really, really small Blinky design. And then we run nextpnr to do the place and route for that. And this will create a .asc file that is a file format used by IceStorm. And then we use IcePack to actually generate a bit stream. So these 3 commands are the entire flow from Verilog to a bit stream. And it's a small design. So it's just like this blinks on an ice stick. So who here has already had any experience with a commercial FPGA flow? Okay, so I'd like to imagine if you take the commercial tool of your choice and run a Blinky design from Verilog to bitstream that you can program, the entire flow, how long this will take. And we will compare it, what you have in your head, with what we have here. So that was 1/3 of a second. And some people will say, yeah, but that's a super small design. That's not the thing that the industry is interested. The industry is interested if it takes like 5 hours or 10 hours to do place and route for a really large design. But I think that's exactly missing the point. The point is that every application is different. And when you have an open source flow, then you can optimize it for whatever aspect is important to you. And if you have a closed tool, then you just have to live with whatever the optimization goals are that the vendor is setting for you. Okay, so that was that. So this is now a much larger design. It's a Pico RV32, a 32-bit RISC-V SoC. Running in an HX 8K. I did already run the 3 commented out commands before, so we can go directly into nextpnr when I run that thing here. Okay, so this is a HX 8K, a 8000 LUT device from the ICE40 series. We can zoom in here. I can select individual things here, like nets, bells. So what I did now was run the packer, this icon here. And you can see the design that we have has about almost 2,000 cells. Next thing in the flow would be to assign a timing budget. And of course, there are more fine-grained ways to do that. But now we just say, make the whole thing run with 50 megahertz, and it's just all the clocks are now constrained to 50 megahertz. Then we need to run the placer. We can actually watch the placer moving cells around. The placer algorithm, as we use it here, is a 2-stage process. In the first stage, we leave the relative placement constraints for stuff like carry chains looser, and then we strengthen this iteratively, and then we reach okay, I can't scroll up while it's running. So then we reach this point here where we legalize them and make sure that the carry chains are actually intact. And from that point onward, we always leave all those constraints intact. And then we end up with a placement and the post-placement timing report. And at least the post-placement timing report looks pretty good for 50 megahertz target here. I'm quite happy with that. Yeah, then we run the router. And the router is fairly fast, as you can see. And we are done. Now we can, if we want, write the bitstream file. Whatever. And we are done. So, why is it not? So this is the ASC file we just wrote. And then we can use the iStorm tools to convert that into a bitstream file. OK, so I guess with that, I'll open it up for questions.
Thank you very much, Clifford. So we have ample amount of time for questions. Please line up at the microphones and remember to have them closely to your mouth so we can understand you. So microphone 1, please.
Yeah, thank you for the talk. I'm curious about one of the things. One of them is what constraint solver do you use? Is it a constraint solver? And is it like a proper one or is it more like a heuristic?
So we are, one of the projects that we're pursuing right now is looking into using SAT solvers for placement. Right now we don't really have working code for that. My personal preference as for solver as that would probably be glucose or cryptominisat. Oh yeah, I recognize you from your Twitter.
So, microphone 1 again.
Well, since the tool generates this sort of a blob of logic in the middle, won't the FPGA overheat in the middle while being basically cold on the outside? So wouldn't it generate a huge temperature gradient?
No. So the temperature gradient is not really. There are reasons why I would like to have things fanned out a little bit more over a wider area, specifically to help with routability. But especially if you give it timing constraints, it like tends to put everything closer together. But I mean, this device, maybe, I would guess it's less than a square millimeter die size, and it has, the temperature should not really vary much. Also, this is an ultra low power FPGA, so it shouldn't get warm anyways. At least that's what the vendor promises.
A question from the internet.
Yes, thank you. Can you modify final placement in the GUI interactive?
Not in the GUI. So you can you unplace things in the GUI? That might be possible. I'm not sure. Where is the cell? Bound cell? No, I mean I can here write, what is it? Unbind the bell and then the name of the bell, which was like this here. X16, Y17, logic cell 6, I guess. And now the bell is available. So if typing this Python command counts as in the GUI, then yes, you can do things in the GUI.
Okay, any more questions from the internet?
Yes. Have you thought about utilizing hardware acceleration as OpenCL or something?
I didn't quite understand the question. Hardware acceleration like OpenCL. Yeah, I mean, I'm not quite sure how it relates to place and route. Because usually when you do OpenCL acceleration, you would like to run it through something like a high-level synthesis tool, and you end up with Verilog. And then you run that Verilog through your regular synthesis chain. Or do you mean using it for place and route? So we did have discussions about that, but nothing concrete right now.
So microphone 2, please.
Hi, so you said place and route is completely timing driven. In Vivado there are also strategies like runtime optimized or area driven. Are these also possible?
So the area-driven stuff is usually more in the synthesis tool. There's not that much what the place and route tool can do. And I would say most of the things we do right now on the synthesis side with users is actually more area-driven, because right now we don't really have the timing constraints in synthesis. So the more embarrassing question for me would be, do we have timing-driven synthesis in users yet? But luckily this is a next PNR talk.
Okay, another question from the internet?
No, thanks.
Okay, I would say this concludes this talk and the Q&A session. So
Let me
let's
just close
so
with, there is an area over in hall 2, next to the hardware hacking area. It's the Open FPGA area. We have white umbrellas that have Open FPGA written on them. So if you have any questions, just come find us there. And we also do beginners workshops with these icebreaker boards.
Okay, perfect.
Now I'm done.
A lot of stuff to be done, so have fun with that, and let's give a warm hand of applause to our speaker again.